So we're going to see how the roots, or we call them radicals, are being simplified. And we considered various radicals, square roots, cube roots, fourth degree roots. And for all of those, we need to find the corresponding power, which means that for exercise like problem 42 here, we need to find the power of 2 because we have a square root of degree 2. So if it's a second order radical, then I'm looking for the second power that will correspond to it, which means that when I try to extract my square root from 49, I can think of it as about a 7 squared. And similarly with number 81, that I can think of 9 squared. So square root and square will cancel each other out, and we're going to end up with 7 divided by 9 as our answer. So the point is we need to find perfect square when we extract our square root. In the problem number 49, we have another square root to extract. It goes with a 64 that I can prepare as 8 squared, and y to the power of 4 that I can also say is a square of y to the second power. So these squares, such as 8 squared, will give us just 8 because they disappear. And similarly, the power of 2 of y, which is squared, is no longer going to be raised to the power of 2. In other words, sometimes people say when you extract square root, then you divide your power by 2, and that's what it is. How about problem number 61 that works with a cube root, with a third degree root that I can also prepare as a perfect third power, and this will be a what? 4. 4 times 4 is 16, and 16 times 4 is going to be exactly 64, but what I need is to have 3 decimal places, because if I go ahead and multiply 0.4 with itself 3 times, then I'm gonna end up with not just 64, but 3 decimal places with that 64. So this will be a 0.064. And we can see that the result is going to be just a 0.4. I say, Alex, are you sure? Can you double check that? And the answer is, of course, let us get our favorite scientific calculator, the Desmos one. So I can extract the cube root, and the symbol for it is right here. So I just want to click on that root and put 3 as an index and extract it from 0.064 and get the answer, which is exactly 0.4 that we produced. So indeed, this seemed to be a calculator exercise, but of course, whenever you have variables involved, then you cannot really use the calculator, you can try, but it's not gonna help. So let me do one more cube root extraction and exercise number 65. So we're gonna be dealing here with a cube root extracted from -1000, which is minus 10 to the power of 3. Notice if I go ahead and multiply negative number 3 times with itself, the result is going to be a negative. So we put 3 zeros because there is a product of 3 numbers 10, and that's what we have here. P to the power of 3 is a perfect cube, so there is nothing I need to worry when I try to extract the cube root from it. But with a q, I can divide the power of 6 by 3 and get q squared. In other words, if I cube that second power of q, I'll get just what I need. So this will be a -10 without a cube, p and q to the power of 2. And this is it. This is our little answer. So the point is, whenever you have a third degree root, then you need to worry about the perfect cubes, perfect third powers. So let us move on to the next section and see more of the radicals at work. And here they talking about very popular statement called Pythagorean theorem. So whenever you have a so-called right triangle with right angle, the angle that measured 90 degrees, then there is a special relationship on its sides that says the sum of squares of those sides that compose this 90 degrees angle, or so-called legs of that right triangle, will be equal to a square of hypotenuse. So this way I get the setting, and they give example with very popular Pythagorean triple of numbers. They say if a is equal to 4, b is 3, then when you use 4 squared and 3 squared and add them together, you're going to be adding 16 and 9, which is total to 25. And notice that 25 is 5 squared. So you can see that the third number, the so-called hypotenuse, the longest side, is going to be 5. So square of 5 is exactly the sum of squares of 3 and 4. Well, this happens rarely. Doesn't happen too often. It's just for special triple of numbers 3, 4, and 5. And that's what they introduced us with in here. So I'm going to scroll down to the end of the section where exercises are, and see they have this Pythagorean theorem in use a little bit in the problems, like say exercise number 19. Let me do one here. Exercise 19 that says you're given the sides B and C. So why don't I produce a picture? And turns out we always call these sides as A, B, and hypotenuse C. So they tell us that B is equal to 18 and the hypotenuse C is equal to 82. Okay, so when I think of this statement of Pythagorean theorem, I will be replacing in it number b with 18, so there'd be 18 squared. Number c with 82, so that'd be 82 squared. And then we're going to find unknown a, the third side of this right triangle. So I'm going to bring that 18 squared over to the other side and see that this will be a assumption that I can calculate, right? Let me go to the calculator. 82 squared minus 18 squared. So the calculator is definitely useful for this exercise. Yes, you can do this by hand, but if you have access to the free calculator, why wouldn't you utilize it? So what about A? Well, looks like 64 is 8 squared, so it'll be 80. And indeed, you can double check this if you extract the square root from 6400, you will indeed get 80, the length of third side of this little triangle. How about that? So we have a little section 7.2 that I just wanted to do a problem from because exercises here are pretty much the same. So I'm gonna move on to the next part of the story that talks more about those powers and everything, and they actually give us various so-called properties of powers, properties of the exponents. So let me take a look at some of these properties and start to get used to them. For example, if you multiply x to the second power by x to the power of 3, then people say the result will be x to the power of 5, because what they want you to do is add these powers. And if you wonder how come these powers need to be added, then you can check out and see what x squared stands for, and also what x cubed represents. And once you see that x cubed has 3 factors of x and x squared has 2 of those factors, then the product of 5 x's is indeed x to the power of 5. And that's what justifies the first formula here in that set. The other very popular formula is when you divide the powers, say x to the power of 3, if you divide it by x to the second power. And it turns out for the answer, I just get x to the power of 3 minus 2, which is just 1, or x only. So when you divide, what you need is to subtract your powers. And I can also visualize this by simply writing the x cubed as product of 3 x's and x squared as product of 2 x's, and then we can cancel pair of those factors of x and indeed just have only x left here for us. So that justifies the formula number 7, the one that is very useful for making a proof for exercise like number 5. So what if I think of x raised to the power of 0? What is this equal to? Well, I can actually think about the same powers, let's say x squared divided by x squared, So the powers going to be subtracted according to the property we just did above. So we subtract 2 and 2, and that's actually how we end up with this 0 power when you divide exactly the same factors. But when you do this, they actually cancel, and all you have is just 1 whenever you divide the same number by exactly the same number, like 2 by 2, you get 1, or 10 divided by 10, it is still equal to 1. So we cancel everything and get 1. So on one hand, I produced number 1 in here, and on the other hand, it's equal to x to the power of 0. And that's exactly what justifies the formula number 5. And that's very interesting, right? 0 power, how come it is given us 1, may not seem to be very intuitive, but actually there is a justification of it. Another formula I'd like to take a look at is a negative power. So if I have x to the power of -2, for example, then I can write the -2 as a 0 minus 2. Can I? I mean, 0 minus 2 is still -2, but this will enable me to write this as a fraction. So we can put x to the power of 0 on the top and x squared on the bottom of this fraction. So x to the power of 0 is equal to 1, isn't it? I can recall the previous exercise and replace my numerator with 1 and see what we ended up with. On one hand, it's a negative power. On the other hand, we bring it down and make it be positive. So instead of power of -2, now I have a +2 power, but in my denominator. So we produce the answer, and that's all we need. So it looks like this bunch of formulas is here, and our goal today will be to start getting used to those formulas, because I know there are lots of them. So we want to little by little to get used to these little formulas. And I hope that you're already familiar with those formulas a little bit. So I'd like to take a look at exercise like number 93 here and see what you do with those exponents when we multiply 5 raised to the power of 4 over 9, looks like. And another factor here will be 5 raised to, again, power of 4 over 9. So we basically have exactly the same multiplication of exactly the same two factors, 5 to the power of 4 over 9. Well, according to the property of multiplying exponents with the same exact basis, I'm going to have to add those powers. So since base is 5, I don't really care what base is, I just copy 5 and then add 4 nines with another 4 nines, and that's how we ended up with 8 over 9. Let me write it a little bit bigger so you better see this. 8 of those 9s, and that's our answer. So the idea is it doesn't matter you have the fractions or whole numbers, you just go ahead and add those powers and get a result. Turns out that this could also be treated as a 9th root extracted from 5 to the power of 8. In other words, the fractional powers we can write as radicals. And that's interesting. Let me do one more here, exercise number 95. So I'm going to try another little exercise to get the 4 to the power of 1/5 raised to the power of 3 on the outside. Well, it turns out that now you're going to need to multiply those powers, 1/5 and 3. And as a result, you're going to get power of 3/5, just like that. Or sometimes people say it's a 5th root from 4 cubed. And since this is exactly the same thing, it wouldn't really matter if you write it or not, because it's the same thing. So you don't need to worry about it. And that's very interesting, right? So you get these various exponential type of exercises. So let me try here one more, problem number 99, that says, take a look at the 9 raised to the power of 4 divided by 5, and then you also put in denominator 9 to the power of 3/5. Well, it looks like the power of 9 will have something to do with those fifths. So I'm going to need to subtract from 4/5, 3/5. And since denominator is the same, I just subtract numerators and get 9 raised to the power of 1/5. You don't have to write 5th root. I just wanted to stress that for just in case. So this is the idea. Now I want to tell you that I started to think of producing a YouTube channel so I can put the recordings of lectures on it, because I know that these recordings, they disappear, right? So disappear, and well, if you try to watch those recordings after 30 days, they will be gone. And since we are going to have our final exam coming soon, it's actually in 2 weeks, we have a final, then some of those recordings will no longer be available. So what I'm gonna do over the weekend is I'm going to get all of the lecture recordings and I will put them on the YouTube channel. My wife has a YouTube channel, and I will, I guess, ask her to use her channel, because I'm not very good at this technology things, but she said she would help me. So I'll see if I could put this in her channel, all those recordings. And that way you can always go there and watch the recordings before the final. And I think that'd be pretty helpful to have them all in one place, right? So you just be able to get the intermediate algebra class, and if you want to, and watch all of those recordings if you need to refresh your memories. I think that'd be awesome help, because again, since our college keeps those recordings only for 30 days, well, I guess the YouTube has more funds, so they keep those recordings. I don't want to say forever, but for a long time. So I think that'd be very, very helpful. But again, I just need to work out over weekend on this, because I'm not very good at this kind of thing. But anyways, I think this is something that our I guess, college students can definitely utilize, because looks like we had an issue with Google. You probably noticed that now Google is cutting off on the memory available for people with its accounts, because now you need to pay for the storage. It used to be free. They used to say, oh, it's unlimited account, but not any longer. Now, if you pack lots of stuff, pictures and things in your personal Google account, they will ask you to pay for it monthly fees, and it adds up. If you pay it only once, like, it's not a big deal probably, but if you have to pay this bill every single month, well, it's not that cheap. So I guess internet is getting more and more expensive, right? Also, same with Twitter. I guess they start accounts that people have to pay for. So, and I'm trying to find the free tools for my students, and I believe that on the YouTube, at least there, you don't have to pay. So that would be useful. So anyways, I'll be working on this over weekend, and we're gonna continue with all of this on Monday. So we're gonna do some more exercises in this section. So I just started it, so maybe I'm not gonna give you a quiz right now. So I'm going to just keep on talking about chapter 7 next week. So I'm gonna stop this recording, and as usual,